definition in the simplest terms is its relative humidity is the measure of the amount of water vapor. So how much water vapor is in the air at a specific temperature compared to the max amount of water vapor air could hold at that temperature. So as an example, if we said that there were 2 cups of water in the atmosphere, so you have 2 cups of water in the atmosphere right now, and the temperature outside is, let's say, 50 degrees Fahrenheit. What that is it's the amount of water vapor in the air at a specific temperature compared to the max amount of water vapor it could hold at that same temperature. So let's say that at 50 degrees Fahrenheit the air could hold 20 cups of water. And again, it holds 20 cups of water at 50 degrees Fahrenheit. And again, this is just an example. This is not true scientific information. It's just a simple way to show you how they use the measurements and the amounts. So you have 2 cups, that's how much water is in the atmosphere right now at 50 degrees. The air could hold 20 cups at 50 degrees. So the given percentage of this would be 2 divided by 20, which is equal to 10% relative humidity at 50 degrees Fahrenheit. So at 50 degrees it had 10% relative humidity based upon the information that I've given to you on your screen. So what does this truly mean? Okay, why are we talking so much about relative humidity and moisture that's in our atmosphere? What it truly depends upon is the actual temperature that is in our atmosphere, how warm or how cold it is outside. And as I've mentioned before, I'll say it again, as air becomes warmer, it can hold more moisture compared to cold air. So, for example, relative humidity at 100% shows that the air is holding all the water it can at that given temperature, at that current temperature outside. And then if you had any additional moisture, so if there was evaporation that was taking place, or that air mass that was over land then moves over, let's say, a lake or maybe an ocean and starts to add more moisture to it, then what happens is you get condensation or precipitation, because as you add more to the atmosphere and it can't hold it any longer, it has to get rid of it, and by getting rid of it, it falls as condensation or precipitation. Okay, and precipitation can be rain, can be snow, can be sleet, could be hail as an example. So again, a simpler connection between them. If you have a relative humidity of 50%, this means that the air that surrounds you right now is filled halfway up with some type of moisture. And that's how much it could hold at that current temperature. So if it's 70 degrees outside and you have 50% relative humidity, that means that the air that is surrounding you is filled up with 50% moisture that has some sort of water vapor in it, and that's at 70 degrees Fahrenheit. And as the temperature increases, that percentage is going to decrease because the air can hold more. It changes the ratio, it changes the math formula, so it causes the relative humidity to drop. So as the temperature decreases, so now we're talking on the other end of it, so as the temperature starts to go down, the amount of moisture in the air doesn't change. The temperature does, which means that the space that's around us starts to get smaller, starts to shrink, and starts to condense. Okay, and when that happens, the amount of moisture is still the same. You still have the same amount of moisture, let's say 2 cups again. But as the temperature changes, the space around us starts to condense and starts to get cool and starts to shrink. And as that happens, the amount of moisture doesn't change, but the relative humidity goes up. The reason why is because the 2 cups that we started with as the example a couple slides ago the 2 cups that the air was holding at 50 degrees Fahrenheit, and now the temperature is starting to change, and the temperature drops to 40, the air can no longer hold 20 cups. The air now holds, let's say, 10 cups at 40 degrees. And when our relative humidity was 10%, 20 divided by, or 2 divided by 20, now it's 2 divided by 10. And instead of 10%, it now becomes 20%. So the relative humidity went up. So here's the relationship. If you haven't seen it, haven't heard it yet. As temperature goes up, temperature increases. Relative humidity is going to decrease. As temperature decreases, it goes down. Relative humidity is going to go up. So again, talking about the same thing. We've already hit the decreases. So as temperature increases, the amount of moisture in the air doesn't change. We still have 2 cups of water as our example. So if the 2 cups and the temperature goes up, so we went from 40 degrees back up to 50. So now we went from holding 10 cups of water at 40, we now can hold 20 cups at 50. And if we were holding 10 cups, our relative humidity was 20%. But now that the temperature has gone up, the space has increased. It has expanded because it's much warmer. And that has now caused our relative humidity to drop because the amount of moisture is still the same. 2 cups of air, 2 cups of moisture in the air. And that relative humidity now is 10%. 2 divided by 20. Relative humidity has gone down. So, there's the long-winded version of what relative humidity is. Let me show you what relative humidity is. This comes from a professor at Middle Tennessee, I think Middle Tennessee State, and he does a really good job of explaining what relative humidity is. So as you are going through this, I'm going to ask for you to take your notes, and while taking your notes, you're going to be asked to draw in some things while you're watching this presentation given by here. You're going to be asked to shade in the different types of cups that he uses. He starts off with some big cups and then works his way down to small cups. And then he's going to talk about as relative humidity increases or decreases depending on the size of the cup based upon what happens to the temperature and then the volume of air. So for each presentation that he gives and each demonstration that he shows, I would like you to shade in the space that's filled with water, and then talk about if relative humidity has increased or decreased, temperature increased or decreased, or the volume of air has increased or decreased. And while you're also watching that, I've provided you with a series of questions. There are a total of 6 questions all in total that can go along with this data table as well. Alright, so I'll turn it over to the professor and allow him to explain what relative humidity is.
Alright, in this demonstration we're going to demonstrate using these beakers and some water concepts of relative humidity. Now remember, the relative humidity is the amount of water vapor, individual water molecules, in a given parcel of air relative to the number of water molecules that could be in that particular parcel of air. And it turns out that the relative humidity really depends on the temperature. Now it's important to think of air a little bit differently than maybe you usually do. Air consists primarily of nitrogen, 78% nitrogen molecules, another 21% oxygen, that's 99%. The other 1% is just a whole bunch of other stuff we're not going to worry about. But it's also important to remember that those molecules of air are not really interacting with each other. And that means that there's something else in the air too. That means there's space in the air. There's room between those nitrogen and oxygen molecules. And we can put another molecule into that space. And the molecule that we're interested in is water. So think of relative humidity in a sense of how many water molecules we're putting in the spaces between the air molecules, the nitrogen and the oxygen. There's so many spaces in a given volume of air. If they're all filled with water molecules, then we say the air is saturated and the relative humidity is 100%. If there isn't any water molecules in it, then we would say the relative humidity was 0 and all the spaces are empty. But that very, very rarely ever happens in nature. So, here I've got 5 beakers. And let's say that these beakers represent a particular volume of air. And let's say the center beaker here represents a volume of air at a particular temperature. And you can see it's about half full of water. If the entire beaker represents all of the space available to put water, it's about half full. So we'd say the relative humidity in this beaker is 50%, because 50% of the spaces have water in it. But what happens as we warm this air up? As air is heated, the molecules begin moving faster. As they move faster, they spread further apart and the volume increases. That basically means we're making more space. And so if we warm it up a little bit, now the air has this volume. It means it's got more space. And the water is not taking up as much of the available space. See, this is not quite half full. The level is lower in that beaker. If we warm it up even more, say to this size, same amount of water vapor, but now we're making even more space, and you can see that it only fills it up a little ways. Certainly doesn't fill it up halfway. But what happens if we go the other way? So, well, when you warm air up, space increases, the relative humidity goes down. Temperature goes up, humidity goes down, unless there's a source of water vapor to put into it. Okay, what happens as we cool this down? Volume is going to decrease, the amount of space is going to decrease, and so now that number of water molecules is taking up more of the volume. Let's cool it down even more. Now we're back where we started at about 50% relative humidity. But what happens if we cool it down even more? Oh, just about full. Now we're almost at 100%. Almost all the spaces are filled with air. What happens if we cool it down even more? And this point where the relative humidity, this temperature, we're cooling the temperature down. When we reach that point where all the space is gone and the relative humidity is 100%, that temperature is called the dew point. This beaker is completely full. If we continue to cool it down, what's it going to do? Yep, it's going to rain. So, when relatively warm air that has a lot of space in it, when it's around a body of water like an ocean, or in the case of where we live here in the state of Tennessee, we get ours primarily from the Gulf of Mexico, that water is going to evaporate into that warm air, taking advantage of all the space that's available, and then as that warm air rises, because it's less dense, begins to expand, begins to cool off. As that air cools, the humidity is going to go up. When it reaches the temperature where the relative humidity is 100%, that's the dew point, then condensation can begin to occur, and if the conditions are right, clouds will form, and as air continues to cool, as the clouds form and thicken, eventually precipitation happens.